So I'm not sure, but I think, okay, so I only have 15 minutes to record. So I'm gonna try to continue in a little bit faster pace here. Okay, the next problems, here we go. Square root functions are one-to-one functions, so we can find the inverse, but you'll see that something interesting is gonna happen when we do that. So again, I'm gonna go through following the same procedure. Hopefully this is becoming pretty boring. So what we notice is that the inverse of a square root function is a quadratic. And again, quadratics are tricky because we have to make sure that we restrict the domain, because the inverse of a square root function is just it's just half of a quadratic essentially. And the reason for that is because you can't take the square root of a negative number and get a real answer. You get imaginary numbers, but those aren't graphed on a real coordinate plane. So we have to restrict the domain now of our answer. We're going to do it exactly the same way. We want the right side. So graph this, figure out where the vertex is, and then write your restriction as x is greater than or equal to whatever that x coordinate is of your vertex, which is going to be -5 just for time purposes. Okay. So we'll do the same thing in number 10. A square root function is one-to-one, so we can find the inverse directly. Swap your x and y and solve for y. Again. So our inverse, again, oh, I messed that up, ends up being a quadratic. And I hope I blocked myself in the... And so we have to make sure that we restrict the domain, which we find by graphing. And again, we just want the right side. Okay, so that is finding the inverse of multiple different algebraic functions. The next few problems that we're going to talk about deal with the graphs of inverse functions, and specifically how the graphs are reflections across the line y equals x. So this is kind of cool. We're going to graph our function, and we're going to find the inverse algebraically, and then we're going to graph the inverse and make sure that it should look the way it's supposed to. So I'm going to graph my original function in red. It's a line with a y-intercept of 3 and a slope of -1/2, which means it's going to go downhill at a rate of down 1 over 2, or I could go up 1 and over to the left 2. So there's our line of our original function. We're going to calculate the inverse now. Actually, let's do this. Again, because it's a line, it is a one-to-one function. We don't have to worry about restricting the domain. We're going to multiply by -2 on both sides. And we get that our inverse is -2x plus 6, which is also a line that is going to have a y-intercept of 6 and a slope of -2, which means it's also going to go downhill, but this time we're going to go down 2 and run 1 instead of going down 1 and running 2. Or we could go up 2 and run to the left. So it might be a little bit easier to see how these graphs are related to one another once we sketch in our reflection line, which is the line y equals x. This has a y-intercept of 0 and a slope of 1, meaning we rise 1 box and run 1 box. So it kind of is this diagonal that cuts our graph exactly in half. I wish I could have drawn that a little bit straighter, but we can see that the blue is a reflection of the red, and the red is a reflection of the blue across that line. Meaning if we were to fold the graph along that black line, the blue would match up with the red and the red with the blue. Okay. This is another example. So again, I'm going to graph first in red my original function, which has a y-intercept of 1 and a slope of -1, which means, again, downhill 1 over 1. I'm not going to graph every single point because that's going to take a long time. Trying to do this nice and neatly. A little scratchy, maybe. Okay. So let's find the inverse. I'm sorry. And this is interesting. We found that the inverse is exactly the same line that we've graphed in our original, with a y-intercept of -1 and a slope of -1. And let's see if that makes sense. Let's quickly sketch in our reflection line, y equals x. Again, just imagine that straight. And we could see that if we folded the paper along that, the blue and the red would match up with the blue and the red. So in very rare occasions, the inverse and the function itself will be the same function. Okay, and the last example, I want you guys to try this one on your own and pause the video here and see how it goes, and then unpause and see if yours matches mine. Okay, so we've graphed the original line in red with a y-intercept of -8, and we're rising 4, running 1. And then we found our inverse algebraically. I did not write it with inverse notation, so I'm going to do that real quickly. But that was also a line, this time with a y-intercept of 2 and a slope of 1/4. And we can see that they are reflections across that line, y equals x, so we found our inverse correctly. One other thing that you can check that's kind of neat is if you were to ever pick a point on your original line, so in this case, let's say this point here at 2, 0, remember the inverse and the original have the x and y swapped. So if this point is 2, 0 on this line, I should have a coordinating or corresponding point on my blue line at 2, 0. I'm sorry, this point is at 2, 0, so I should have a corresponding point at 0, 2, which I do. Let's check another one. This point's at 1, 2, 3, 4, -4, so I should have a corresponding point on my blue line at -4, 1. And I do. So anyway, just some cool little tricks. That's it. I have made you listen for long enough. If this was not enough, please see me on Monday or make an appointment. And thanks for your attention.